Good morning. I'll continue with a little bit of nuclear physics. I'm picking a path through nuclear physics, just looking at all the essentials. Now, the last day I established notation. I also worked out the mass of one atomic mass unit, which I took to be the mass of any nucleon. Now, the neutron has a slightly different mass to the proton if you examine those masses more closely. So this is kind of a rounded off atomic mass unit. The mass of the proton, the mass of the neutron, or one atomic mass unit. Sometimes it used to be written in the old days like this. I'm writing it MU at the moment. I don't know where I got that notation from. But 1.66 by 10 to the power minus 27 kilograms we'll take to be a close estimate to the extent of an atomic mass unit. Now, this morning I'll work this out also in electron volts. I don't like using electron volts. Particle physics physicists love electron volts. I like to stick with the essentials. There's more digits, you have to write them down, that's okay. Anyway, so the first thing we look at, we're going to work out the energy of this thing, by the way. The energy of this is just mc squared. This multiplied by c squared. But we'll do that in a minute. Now, if we look at an alpha particle, experimentally, 6.6446 by 10 to the power of minus 27 kilograms, there it is there, is the mass of an alpha particle. Ionize a helium nucleus and you get an alpha particle. So I use alpha particle and the helium nucleus interchangeably. 2 protons and 2 neutrons. Atomic mass number 2 and atomic weight number 4. Wherever I put it, I don't know. I didn't put it anywhere. It's easy to visualize it. 2 protons, 2 neutrons in a nucleus makes up the alpha particle or helium nucleus. Okay, count the protons and you get the atomic number. Count all the nucleons and you get the atomic weight. I call it atomic weight. Atomic mass is more correct. So, when you take the nucleons and put them all together and they're there as a nucleus or an alpha particle, the mass of them is different than if I took the individual masses of a proton, the 2 protons together, a neutron, the 2 neutrons together, and added them all up. It's different. Let's see how different. Okay. Where did I get it? Okay, so the mass of the helium nucleus is 6.6446 by 10 to the power of minus 27 kilograms. Okay? If I take a proton, and 2 protons are in there, and the 2 neutrons, and add up the particles all together, I get a bigger number. Look, 6.6950 is bigger than 0.6446. Let's subtract them. So this is the mass of the helium nucleus from the sum of all the constituents, and I get 0.050 by 10 to the power of minus 27 kilograms. We'll call that the mass defect. The difference in masses between an actual measured nucleus. We measure that in the thing called a mass Bainbridge mass spectrograph. Yeah, you throw the particles into this magnetic field and they make a curve, and you measure the radius of curvature of that to find the mass of that particular nucleus. Okay, now, so this is the mass defect. There's a thing called the binding energy. The binding energy of the nucleus is what holds the nucleons together. It's to do with the fact that adding them all up separately, it's bigger than if you just had the whole nucleus together. So the difference in mass is made up by the binding energy or the mass defect. This is the mass defect. Where is it? Here. The mass defect. And the energy associated with that mass defect is what we get if we go mc squared. So there's the mass defect, 0.050 by 10 to the power of minus 27 kilograms. Multiply that by c squared. C squared is 3 squared times 10 to the power of 8 squared, which is 9 by 10 to the power of 16. C squared. 9 by 10 to the power of 16. Meter squared over second squared times kilograms is joules. Kilograms, meter squared over second squared are the units, the base units for the joules. And I have here 9 5s 45, so 0.45 by 10 to the power of minus 11 joules. That's the binding energy of the helium nucleus. Look in a book and you might get a different result. You see how it's done. I have probably slightly different numbers on the board than somebody else writing a text might have access to. One way or another, I looked up a book to find the experimentally determined masses of the protons and the neutrons. I found the mass of the proton in some book to be 1.6726, which is bigger, by 10 to the power of minus 27 kilograms. I found the mass of the neutron to be 1.67492 by 10 to the power of minus 27 kilograms. I'm not sure how they find the mass of a neutron. Basically, it's easy to find the mass of a proton. You throw it into an electric field or a magnetic field. It's charged and it has a certain trajectory. And you study that trajectory to find its mass. But a neutron is neutral. I don't know how they find the mass of a neutron. I think you could use a helium nucleus and see what the... Yeah, that's how you could probably find the mass of a neutron. Use a helium nucleus or an alpha particle and examine its trajectory in a magnetic field. Okay. So, what next? So that's the binding energy. Sorry. The other way around. The binding energy of the helium nucleus. So we're on a path towards several different things. Okay, so every time you examine a nuclear reaction, you look and check the mass difference between the products and the reactants, okay? So that mass difference will give you the energy if you multiply it by c squared, and that's where the source of all this energy is. So when we come to study fission, which is where we're heading, we're going to look at the fission of a plutonium nucleus and also the fission of a uranium-235 nucleus. And we'll talk about why we're looking at the uranium-235 nucleus in a minute when it comes up. It's to do with the fast neutrons, slow neutrons, and intermediate energy neutrons because, well, we're leading up also to the Manhattan Project. So, let's see if there's anything I can talk about there worth talking about. Not really. I can clear the board with that one. Keep that in mind. I'll keep this on the board. Now let's look at E. Of the energy associated with one atomic mass unit, the energy of a nucleon. So, multiply this by this. 9 6 is 54. 9 6 is 54 and 5 59. 9 1's 9. Now, 27 and 18, let's see. 2 and 7 is 9. Let's see, make sure I got this right. 1.49452 by 10 to the power minus 10. Sorry, I didn't do that right. So that's the energy associated with one atomic mass unit, and it's just as a record I stuck it up there. Now, in MeV, when we convert this to MeV, the mass of a proton, is approximately, well, it's 938.272 by 10 to the power of 6 electron volts. 10 to the power of 6 electron volts is called a million electron volts, or an MeV. 1 MeV is 10 to the power of 6 electron volts. So the mass of a neutron is 639.565 MeV, experimentally determined. Not the same as what we used I found this number using Avogadro's number and the mass of carbon-12 nucleus. And we got the binding energy of helium. Let's convert this to electron volts now. We'll use the spray. We'll convert this to electron volts. That's what we have, the binding energy of He. We call this binding energy. For helium. Okay? So that's the number of joules, and we go 1 eV Now, for converting from joules to EV or EV to joules, you need a unit factor which cancels out the thing you don't want and introduces the thing you do want. I have a whole project on converting things in one set of units to another set of units. So a unit factor would be like this. Another unit factor would be this. So this one converts joules to EV, and this one converts EV to joules, because they are both unit factors. Now up here we have this many joules, 10 to the power of minus 11 joules, and we want to convert that to EV. So we multiply by the unit factor needed for it. We want to get rid of the joules and end up with EVs. So we have to use that particular unit factor, this one. Okay, so let's use the calculator for that. And I got that many EV. Now 1 from this is 8, 10 to the power of positive 8 EV. Okay? So 10 to the power of positive 8 EV is going to be 0.28 times 10 to the power of 2 times 10 to the power of 6 EV. And in MeV, it's going to be this. 28 million electron volts. And that's what we were setting out to do. Now to demonstrate that, I could go ahead and convert this to EV and this to EV using the same unit factor. Alright, so you just have to put the numbers in on your computer and make sure you don't make a mistake. Now the next thing we're going to do is we're going to look at fission, but I'll keep it as a separate class, and here's what's coming up. I'll leave that there in case I need. So So we did what we wanted to do today. That's done. All right, I'll leave that there. Now, if you look at Bob Server's lectures that he gave in Los Alamos in 1944, I forget what year, 1940, could be 45, 44 it would have to be. It begins with looking at the energy of one fission of uranium-235, okay? Now, there are different kinds of neutrons available to fission something. What does that mean? You take some nucleus X, and throw a neutron at it, and the neutron comes in, hits it. Now, Bohr has his liquid drop model of the nucleus. The nucleus oscillates and eventually splits into two parts. Now, suppose the atomic weight of this one is Q. This is going to be approximately Q over 2, and this one's going to be approximately Q over 2, but not exactly, because any fission products are possible. So you're going to get the fission products, some neutrons, and some energy for every fission episode, every fission event. There's going to be an energy per fission, which in the case of uranium-235 is approximately 175 electron volts per fission, okay? Now, what are we going to be looking at? What reaction? Actually, I'll put it on the board. We're going to be looking at this one. And each fission will have an associated energy of it, the energy of fission, like it's going to be the order of 200 eV for every fission. So in this case here, the neutron comes in, bombards uranium-235, which is fissionable for so slow neutrons. Now the normal uranium is uranium-238. But for every sample of uranium, you get 99.3% uranium-238 in a sample, and 0.7% of it will be the fissionable uranium-235. Now the job of, let's say you want to make a weapon, is to enrich the uranium, as they call it. That means you increase the percentage of uranium-235 to make it fissionable, so that you can create what's called critical mass. I'll talk about that later. And the job of Los Alamos, like Oppenheimer was in Los Alamos mostly, Feynman was down there, Hans Bethe and a whole lot of other people. They were the theorists and the experimentalists working out how to actually make the weapon. There were two other main places, Oak Ridge in Tennessee and Hanford in Washington State, and their job was to isolate uranium-235 and in another case make plutonium, because they set about making two bombs. One was the gun type bomb that was dropped on Hiroshima, and that was the uranium bomb. They didn't need to test that because they knew it was going to work. But the other one was the implosion bomb. The implosion bomb required you to have a sphere and shrink it to get what's called critical mass. We'll talk about that later. and you shrunk that sphere, you imploded it using explosives. A fellow called Kistiakowsky designed the explosives. He was an explosive chemist, expert. So many different fission products are possible. I just took those to do our example. Molybdenum-98 is one large nucleus, and xenon-136 is the other large nucleus, and a couple of extra neutrons are made plus the energy. Now what do these two neutrons go along and do? These two neutrons, they go and bounce into some other nuclei nearby, and those subsequent nuclei go on and make more neutrons, so therefore you get an expanding chain reaction, a fire if you like. And that chain reaction can lead to an explosion or just a reaction. In the case of an explosion, of course, you have to have about 10 to the power of, you need about 80 generations. You like 2, 4, 16, 32, 64, 128, 256, 512, 1024, and so on and so forth, 2 to the power of. So you need 80 different generations to have that chain reaction really take off. So that's the general idea of what's coming up. We'll look at that in more detail when we get the time. Is there anything I could say about that? I'll talk generally about the Manhattan Project. It's something I know a little bit about. I've done a lot of reading on. And I had the great pleasure of spending time in the company of one of those researchers, I.I. Rabi, and I had lunch with him. And of course my first teacher was one of them too. My first teacher was David Bohm, who was Oppenheimer's student. Okay, Oppenheimer was a bit of a communist. Bohm was a bit of a communist. A whole lot of them were actually. They were coming out of the woodwork, and that's why you ended up with a lot of spies in Manhattan. A fellow called Greenglass. That wasn't his name at all. He was a serious spy. Klaus Fuchs, and I don't know who's the other one. There's another one. There's 3 main spies anyway in Los Alamos, but there were probably dozens. So that when Roosevelt went to tell Stalin about the possibility of an atomic bomb, or that America had one, Stalin was nonchalant because he already had that information. He knew exactly what was going on. Oh, that's a big tragedy anyway. They gave away the secrets, and then next thing the Russians had it. And the Russians would have been 20 or 30 years behind if they didn't get those secrets handed to them on a plate. So that's all coming up. We'll look at this reaction, the energy of it, and we'll look at how much uranium-238 you'll have to fission to, let's say, make an explosion of 20,000 tons of TNT. Okay? So they tested the plutonium bomb out in Alamogordo, New Mexico, in a place called Trinity. Oppenheimer was there, and the whole project, was really managed by a fellow called Leslie Groves. He was a general in the US Army. Some people say Oppenheimer is the father of the bomb. Leslie Grove is. Leslie Grove followed by Oppenheimer. I mean, they were a team, and they did work well together. And Groves kind of knew Oppenheimer had communist leanings, because they all had these people checked out before, and Oppenheimer nearly didn't get the job because security people didn't want them on the project, want him or several other people on the project. The problem with that was, when you started looking at all the other candidates, they were borderline communists too, at least people who could make the bomb. Long story, we'll leave that for the next day.